So the next example is as shown here. So we say the diagram shows a cuboid whose vertices are O, A, B, C, D, E, F and G. Vectors A, B and C are the position vectors of A, B and C respectively. We're trying to prove that the diagonals O, E and BG bisect each other. So this problem is really about two things. One is showing that the diagonals actually meet at all, and showing that that point is halfway between O and E and halfway between B and G. Okay, so to start with, if we imagine some point on O to E, we could express that point as, let's call it M. Then that point, because it's somewhere on O to E, it's going to mean that O to M is some multiple. So I'm going to use mu here. We often use Greek letters when we're dealing with vectors. Thanks, pi. Sorry, that's a cat just getting in the way. Anyway, O to M must be mu times by O to E. So it's just somewhere along there. We also want to think about if that point's also on B to G, then there must be some way of getting to it via going from O to B and then from B to G. So let's say O to M can be equal to O to B plus some other multiple, lambda, of B to G. What we're hoping to show is that we can actually find values where these points will coincide, and we want to show that they're both equal to a half, because then it means that's going to be the midpoint of BG and O to E. Well, to start with, we've got to get from O to E, we could go from O to A to G to E, for example. So O to A is just A to G is C, and G to E is B. So in other words, O to E is equal to A plus C plus B, or if you're obsessed with the alphabet, that's the same as A plus B plus C. And then we want to do something similar with B to G. So if we think about how to get from B to G, we could go from B to O, up to C, and then to G, for example. There are other ways we could go around the shape. So B to G is equal to minus B, because that takes us back to O, plus C, that takes us up to C, and then C to G is the same as A. So it's minus B plus C plus A. So if you go back to what we were looking at earlier, so this bit about how to get from O to M, well, we said it's equal to mu times O to E, and same as O to B plus lambda times B to G. Well, mu times O to E is just going to be that vector we got a moment ago, but all of A, B and C multiplied by mu. So that's mu A plus mu B plus mu C. Then in a similar kind of way, we had O to B add lambda B to G. Well, that's the same as O to B, which is just B. Let me write all this out. Plus lambda times all the things we worked out for B to G, which was minus B plus C plus A. So we can have plus minus lambda B plus lambda C plus lambda A, which we could actually simplify a little bit to mean that's really lambda A plus 1 minus lambda B plus lambda C. And so if we want those two diagonals to intersect each other and be at the midpoint, what we really want is for this bit and this bit to be the same point. Well, that's going to be true if mu and lambda are both equal to a half. And that's really what we're trying to show, because we've now shown that that point is halfway from O to E and halfway from B to G, and it's the same point. So therefore O to E and B to G intersect, and because it's in the middle, that means they must bisect each other. And that's that.